let's go ahead and continue. So we've talked about some of the potential dark sides of machine learning and some of the reasons that I think it's very important for practitioners using machine learning to be very aware of some of the things that can go wrong. Let's continue that analysis. So far we've only really been talking about things that can just go wrong accidentally without even bringing a deliberate malicious attack of any kind, right? Nobody had to deliberately say, I want this machine learning model to be biased. It was just, likely accidentally biased based on the biased data that it was fed. But let's look now at some of the more adversarial situations when actual adversarial behavior comes into play. And one of the interesting examples was the way these natural language processing systems, voice analysis based systems such as Alexa, people discovered they could be hacked and trolled in different ways. For example, there was an incident where saying, the right things, Alexa, please order me a dollhouse, or, something, I don't remember what the exact phrase was. Well, this was a command to Amazon to buy a dollhouse. And when they discovered that, when this pre-recorded message was played, or in this case, a 6-year-old asked this perfectly innocent in principle question, asked, can you play dollhouse with me and get me a dollhouse? Then, Amazon Echo obliged by ordering a dollhouse, right? And, well, is this an adversarial machine learning environment? Well, when you think, who's the adversary here? Who's the attacker? Well, the attacker is a 6-year-old, right? Yeah. And the attacker maybe wasn't even planning to attack, but per se. But this is one of the interesting ways that things can go wrong for when you put too much power in the hands of these kinds of algorithmic systems. So, of course, that's just the starting point of things going haywire. A more impressive incident was in 2016, the TASE system from Microsoft Research. Did any of you have a chance to see this or interact with it? Just try. Yeah. So this was, we'll get back to that in a minute. Well, their goal was to use machine learning and interaction between their machine learning model and this big crowdsource and just lots of people to improve the understanding of conversational language. And they said, well, hopefully TASE responses should become more natural over time. It'll learn to be a better person, right? But that's not exactly what happened, as those of you who remember it well know. So instead, it basically attracted all of the trolls on the internet who decided, well, let's see what we can get this thing to do if we talk to it in the right way. So it basically attracted a lot of trolls who basically just deliberately exposed it to a lot of hate speech and other things, and basically they, collectively, this human army of self-elected human troll army turned it into a misogynistic and racist, evil AI, basically, right? And and it's all, probably from the trolls' perspective, it's all in good fun, right? And then, of course, MSR was forced to shut it down very quickly, so it didn't actually last long before they, had to take down that experiment. So You know, and this was, you know, human-generated malicious input, and not even particularly coordinated. Just a lot of, you know, a lot of people wanting to, you know, trying to be a little mischievous, have fun with this this thing probably. And so, but you know, collectively, you could count it as an attack, a malicious input. So, you know, this leads to really critical questions that we have to think about in any machine learning system, especially any machine learning system that's going to interact with real humans or take input from the real world, which is, you know, practically any interesting machine learning system. You know, how does it interact with humans? What can go wrong? You know, depending on the data, if a malicious attacker feeds inputs maliciously, or if a crowd of attackers provide, you know, different kinds of malicious input, right? So, you know, kind of how do we ensure the security of machine learning-based systems in these kinds of scenarios, in malicious environments? How do we teach machine learning systems using public data, but in a way that doesn't incorporate, you know, kind of the worst of us, that just reproduce and perpetuate the biases or the, you know, kind of the trolling behaviors of the kind of the worst people or the worst behaviors that interact with. And, you know, how do we in some sense democratize this in a safe and fair and secure way, right? So, and so that's a big, you know, ongoing question, a very hot, important topic of research, very much unanswered. So let's look at some of the relevant threat models. You know, what can go wrong, and where? What's the, you know, and in thinking about the threat model, we have to consider what's the attack surface. What, you know, through what paths can the attacker potentially operate? What are the capabilities of the adversary? You know, can they just inject a little bit of bad data or a lot of bad data, like the you know, the troll army in the case of Tay? And what's the goals of the adversary? Does the adversary necessarily have a coherent goal, or is it just selfishness, or you know? So you know, so all of these things potentially change the situation. So if we look at the abstract, you know, pipeline, the machine learning pipeline. You know, we have inputs coming from the physical domain, getting into digital representation, going through the machine learning model, and then finally going back out and affecting the physical domain again. So, and keep in mind, adversaries can potentially be anywhere in this process. So adversaries can potentially affect, you know, jigger the sensors, you know, you know, change the sensors inputs. You know, how many of you have seen one of the bazillion Hollywood movies where somebody got around a you know, state-of-the-art surveillance system by putting a photo of the hallway in front of the camera, right? So yeah, you know, of course that's the simple version, but you know, anywhere you have real-world sensors, you can have somebody manipulate the physical world sensors to fake the inputs or do something. Make them behave in a different way at the physical domain even before it goes into the system. Then you've got the digital representation. Once it's in the system, maybe someone with access to the devices or access to the data sets that the devices collect before it goes into the machine learning models. If you can manipulate it in there, you know, on its way in the digital domain, there's all kinds of other things that an attacker can potentially do. There's things that can happen basically in the machine learning process itself, on the input side or on the output side. So you can corrupt the model or tamper with the outputs. So, and this is not a complete list of what all the attackers can do. It's just a sample, right? So the point is, you have to think of, you know, all the potential places in the process where data or the process could be tampered with, and what's the risk? What are the risks in those situations? So, and then you need to think of, what are the likely capabilities of an adversary? What's plausible that that an attacker might be able to do? And how much do you think the attacker might know about the machine learning system? So there are what we call black box attacks, where we assume the attacker cannot see into the machine learning black box. It can't actually see the learned model, but can only jigger the inputs and outputs, or maybe even just observed. So a weak attacker might only be able to read the training data, for example, and can't see into the black box of the machine learning model itself, but still might be able to do something just based on that limited information. An attacker, slightly stronger attacker, might be able to inject malicious inputs to change the model, but again doesn't necessarily know what's going on, see what's going in the black box. A still stronger attacker might be able to modify the data and the model and actually see and understand and use what's going on in the machine learning system to optimize the attack. And then at an even more sophisticated level, an attacker might actually be able to corrupt, for example, the logic of the machine learning model. Say, well, the standard machine algorithm has this neural network that does these processing stages. Well, we're going to tweak these neurons to compute this other thing instead of what they're supposed to do, right? So there's, again, a huge range of potential attacker capabilities to think about in terms of what the risks and might potentially be. So let's look at the the training phase. So in any machine learning system, you got to train it somehow. What might go wrong there, right? So if an attacker can access the training data, so this is a pretty weak attack, weak attacker, but the attacker, the attacker can only look at the training data and maybe can't see into the black box of the machine learning model, but the attacker can still create their own machine learning model off to the side. And if it uses similar technologies, and many of these machine learning technologies are pretty similar, it might even be using the same service. It might be using, the attacker might rent Google DeepMind, to run their own model that's very similar to the victim, to the model being attacked, that's also hosted on Google DeepMind potentially. So it might be similar or even identical technologies that the attacker can kind of create a mirror model and fiddle with and use that to test inputs and try to figure out what kind of bad things we can do before actually submitting them to the live system under attack, right? And so that's just a start. So then if the attacker can potentially influence the training data, inject bad or biased data, there's a lot more than the attacker can potentially do. And then, of course, if the attacker can actually fiddle with the logic of the system itself, then that can be an extremely powerful attack that might not be readily detectable either if the attacker is careful. So that's just the training phase. Let's look at the inference phase. So this is where the black box versus white box comes in especially. If the attacker can't see into the machine learning model, then what the attacker can do is send inputs, potentially, if the attacker can inject bad data, and look at what comes out, right? And the attacker can, often submit queries, try to probe what is this model from the outside, and potentially use that to infer vulnerabilities. And this often exploits the transferability property, the fact that if you build a model, a second model using similar data as the first model, or even using the outputs of the first model for a bunch of samples, you're likely to get a somewhat similar model that makes transferable decisions, where a new model that will make most of the same predictions as the original one did, for most of the same inputs, right? And that's what machine learning is supposed to do. But this transferability property makes it, even for fairly weak attackers that only can see the attacked model as a black box, the attacker still gets a lot of power. And of course, if the attacker can actually see into the box, can actually see the neurons firing and look at what the dependencies are, that of course gives the attacker a whole lot more power, and attackers can potentially mount the same kinds of attacks as in the black box model, but much more efficiently, maybe orders of magnitude more efficiently with less computation and less time. So, and what are the adversary's goals? Again, there's a huge range of things that an attacker might do or might want to do. One is attacking confidentiality or privacy. So one of the properties that people tend to hope a machine learning model has is if you make the model, if you train the model based on a whole bunch of private data, like think of machine learning models used to treat diseases or diagnose diseases. And a lot of people, a lot of scientists and doctors want to use AI for medical purposes. This is, in principle, a really good thing, it can help spot signs of some disease early, or spot predispositions to some disease based on your genetics or things like that. So, and there's evidence that this could be very possible, but you hope if the machine learning model is trained on a bunch of genomic data or a bunch of potentially privacy sensitive medical data on a bunch of people, hopefully once all of that data is digested in the model, you would think and hope that doesn't actually contain, the resulting model isn't privacy sensitive anymore. It hopefully doesn't any longer have a identifiable snapshot of me or you or any particular person. But that expectation can fail, and this has been demonstrated that it's very possible and sometimes happens that when a machine learning model is trained on a bunch of private data, a lot of that private data stays in the model, and someone who's looking to making queries, to asking the model the right kind of questions, can actually identify whether, for example, whether a particular person was or wasn't in the training set. And if they were in the training set, potentially use the model to infer some other privacy-sensitive characteristic of that particular person, right? And so research, there's been research in this space, both the attacks, the risks of this. And this boils down to, in some sense, into accidental overfitting of these models. The models are supposed to generalize, but in fact they're just overfitting on the private characteristics of particular individuals, and then that makes the model fail in terms of privacy. But then, of course, that's one type of thing the attacker might want to do. Of course, the attacker might want to attack the integrity, make wrong decisions deliberately, induce outputs of the adversary's choosing for whatever reason. And then, finally, the attacker might want to attack its availability, just make no meaningful output or decision, right? So just swamp it in noise, and that might attacking availability or the utility is often a lot easier than actually making it make a specifically wrong decision. Just swamp things in uncertainty or create no answer. So, and there's been some really interesting demonstrations of the potential power of attackers. In fact, one of the researchers who did this, was involved in this really interesting work, was just gave a talk here recently. How many of you saw Nicolas Paperno's talk? Well, you missed out. So it was just in the past month or so. Anyway, so so a number of researchers demonstrated that for example, if you take a machine learning model that's trained on a bunch of images to recognize different types of animals, and so this picture, on this picture to the left, the machine learning algorithm recognized as a panda with 57.7% confidence. Now, the researchers showed that by adversarially injecting a very, very small amount of noise, represented by the image in the middle, and adding that to the original image, producing the image to the right, which to you and me it probably looks like the same picture, right? But to the machine, this particular machine learning algorithm, that completely changed the machine learning algorithm's results. So the machine learning algorithm now says 99.3% confident that it's a gibbon, right? And they showed all kinds of other demonstrations of this form, that if you can, and I think in this case, this was a white box model where they were actually looking into, into what the machine learning algorithm is doing, and you're optimizing, you're taking that image and optimizing the selection of this noise image precisely to see what the model under attack is doing, and kind of optimize it for this worst case, to kind of optimize to cause the model to come up with this particular adversarially chosen wrong answer, right? So now, yeah, and so it's been shown that this is very readily feasible in all sorts of situations, especially in the white box domain when the attacker can see into the model. Another example, common machine learning problem: recognize handwriting. Classify these into particular digits, 0, 1, 2, 3, and stuff like that. And then, researchers showed that just by adding a little bit of distortion, it can completely change the classification. So, so the point is here, for any given input class, the attacker can just add a little bit of noise, the right pixels here and there, in order to cause any input digit to be misclassified as any other output digit, right? So, in other words, kind of with this adversarial application, you want the machine learning algorithm to take this number input and produce an arbitrary other number output. Just, here's the thing. Just pick the number you want and pick the correct matrix cells, based on the number that you see on the page and the number you want to come out of it. Add a dot here, a dot there, a dot there, and then bingo, the machine learning algorithm misclassifies it as that other digit that you wanted. Right? So, yeah, so these techniques are very, very powerful and general, and also fairly worrying. For there's a lot of people have recognized some of the dangers that that this kind of adversarial effects could create, in the real world. For example, there's a huge amount of interest in machine learning for automated vehicles. Self-driving cars, huge topic, and none of these self-driving cars would plausibly work at all without machine learning, without modern machine learning models. But it's scary, because in that context, if what the car sees can, for example, the car sees a road sign, then it's been shown that by just modifying those images just a little bit, changing the sign of the image a little bit, it can completely reclassify what the car thinks it's seeing. So change the the right turn sign into a road curve sign, or change the people at work sign into into something completely different, right? So, well, and one more comment. I mentioned, that these attacks are easiest in the white box models, of course, but they're also, it turns out, they're very possible in the black box models as well, even if the attacker can't see into the machine learning algorithm. It's less efficient, but an attacker can still often use the transferability property and just probing, queries to come up with similar effects. So, what are some of the defenses and countermeasures that can be deployed? So, again, this is kind of an ongoing question. We don't have full answers on this yet, and I don't think we have complete or foolproof defenses yet in general. Often a lot of these adversarial approaches depend on using machine learning to attack the machine learning system, and that depends on having a lot of adversarial training data, being able to make a lot of queries, to make a lot of tries and a lot of optimization on that. So there's a possibility that so we can once again use machine learning to defend the machine learning model against the models against the adversarial machine learning systems. For example, by creating a lot of adversarial models and then training the original model to not to be fooled by the adversarial models, right? So. To play the attack game and then use machine learning to make the actual refine the actual model to be able to defend against those machine learning created attacks, right? So, and there is some evidence that that is maybe effective, but there's no proof that that's that invites the question, well, what if the attacker just adds one more layer? The attacker gets the result of that. Can the attacker find yet another way to attack the, kind of the defended model? Does it really inoculate the model against those attacks, or does it just make the attacker's life a little harder or less efficient? Then there are other approaches like defensive distillation. So, you might train a model twice. You feed and you feed the first. You train one deep neural network and then feed that deep neural network's outputs into the second one. And then hope that that perturbs the model enough to make it difficult. It kind of obfuscates the logic of the systems going through to disrupt the transferability of the model or the connection of the model to the original data set, and makes it hopefully harder for an attacker that has the original data set to figure out what the actual model is, or to do adversarial things. So again, this might be a slight protection for certain things, but it's clearly not complete protection. And all of these techniques are still breakable by attackers with a lot of computational power. They generally, kind of increase the difficulty of the attack, but don't eliminate any of the attacks. So, what are some of the problems with current defenses? Many of them are static instead of adaptive. They, assume that, a very common approach to these defenses is assume a particular attack. We've observed this attack. Let's assume the attacker is only doing that. Well, we can create a defense for that attack. But then this neglects the fact that in real life, you defend against that attack. Well, the attacker is just going to switch. A real, intelligent attacker is just going to switch and do something else, right? The attacker can always one-up a particular defense against a particular attack, right? And so, you know, in practice, it's extremely hard to find good general adversarial sample adversarial machine learning defenses. We don't have good theoretical models, basically nobody knows how to reason in general about, you know, for a particular defense, are you getting general defense against a whole class of attacks, or are you just protecting against a particular static set of known attacks and kind of leaving the door completely open for the attacker just, you know, taking the next step and working around those defenses, right? Yeah, let's skip that actually. So some of the there has been some progress in limited cases. So going back to the privacy problem, so I brought up the problem of you know, an attacker who wants to compromise the privacy of people whose data was used in a machine learning model, right? So there's been some interesting research by colleagues of ours looking into that problem, and you know, they confirmed that indeed when a model is you know, trained on private information, it's often possible to violate the basic the patient's privacy by making queries to the model that end up revealing with fair certainty at least whether or not that patient was in a known patient was in the model, and sometimes reveal more privacy sensitive information about that patient. And so let's see, do I have? Yeah, and so they studied, they studied this in the black box setting. They were actually attacking models hosted in, I believe, Google DeepMind, where they didn't actually have access to the models, even as researchers. So they were, you know, as researchers, constrained effectively to the black box model. And then they asked questions like, you know, do model predictions leak information about the training data? And is it possible to find out if a given data record was part of the training set? And that's what we call the membership inference problems. And the observation they found is that machine learning models tend to overfit their training data, which means that you know, they not only learn you know, kind of general facts about you know, the data set, you know, facts that have several data points worth of support for it in the infant model, but they also learn facts that don't generalize, that are specific to a particular person whose data was used. And then they looked into how to exploit this overfitting in ways that can you know, can reveal privacy sensitive information in the model. And the way they did this is to basically use machine learning against itself, right? So you know, there was a model that they were attacking, so that was hosted in the Google Cloud platform. And then what they did was they trained a new model that basically optimized to answer classification queries of the form, is a person with this description in the training set of the original model? And they use the answers of the original model. They use the original model. So to train the new model, this new privacy violating model, they basically have the new model go submit queries to the old model of the form, for random combinations of patient attributes or people attributes, they say, okay, this random combination of people attributes is a person matching that description in the training data set, yes or no? And kind of the new model is supposed to just produce yes or no answers. And they're training the new model by going and asking the original model, is this or that person in the training set? And the original, they know the ground truth of that in that case. So they have a bunch of inputs that are and a bunch of inputs that aren't. I think they divide it into two and only use half, and then train the second model based on that, right? And so they create all these shadow models to attack the thing. And then they can go back and use that attack model. The attack model basically figures out through machine learning how to spot the characteristics of for a general potential input is how to infer whether that particular person more likely is or is not in the training set. Right? So basically they're training a machine learning model to violate privacy by training it on an existing machine learning model, if that makes any sense. Right? So very crazy fun work. So they showed that this can be surprisingly effective. For example, they showed this both on Google's and Amazon's platform. On Google's platform, using this ML as a service, they were able to train an attack model to provide a 94% accurate answer as to whether a given input, a given person was or was not in a training set. And this basically means that Google's model is hugely overfitting. It's learning way too much about any data you're putting into it, basically. It's learning a lot of completely non-generalizable and privacy-sensitive data along with the generalizable and kind of good stuff that it's supposed to be learning. And so they observed that there are potential defenses to this, and in particular measures that reduce overfitting techniques. And there's a big topic. This is a big topic in machine learning space. How do you prevent machine learning models from overfitting? How do you make sure that what you've learned is really generalizable, comes from multiple data points worth of evidence and is not just overfitting the specific characteristics of one individual or something. And so anti-overfitting techniques such as regularization and others can help. But it's still very much an open problem. Yeah. And so there's a lot of continuing work in this, continuing work both on the attack space and the defense space. For example, another question is, can you, if you consider the machine learning model itself to be confidential or proprietary, and a lot of companies do, a lot of, data is gold, as they say these days. If a company is, and one of the selling points of Google's and Amazon's hosted machine learning environments is they say, okay, tell companies, okay, you can put your data in our platform and train a model based on it, and then give your customers the ability to query that model, and they won't trust us, they won't learn the data that you put in the model, and they won't even learn the model because the model is your proprietary gold. That's your competitive selling point. But is that true? Is Google and are these platforms really protecting their companies, these models from getting stolen, right, and reproduced elsewhere? And so another thread of privacy research is exploring, well, to what extent can a black box attacker who can only query a model and observe the outputs, can they replicate the model? You know, kind of do enough queries to basically create a second mirror image model that's, you know, more or less equivalent for most purposes to the original model, and basically amounts to stealing it. Even though they never actually saw the neurons or the specific configuration, they can create a good enough copy, right? And so, you know, of course, there's various scenarios in which this is easier or more difficult. You know, lots of issues, and again, you know, it's still very much an open problem. Okay, so that's a general summary of some of the interesting, both, you know, kind of the dark sides, unintended consequences of the widespread use of machine learning, as well as, you know, what can go wrong, and some of the incomplete defenses we have when we have actual adversarial interaction with machine learning systems. So I'd say kind of the most important takeaway points. So of course, ML is a very powerful tool. We're not going to kind of convince anybody to stop using it. It's, you know, so useful. You know, we can't even really start, but we got to be extremely aware of the dangers. First of all, that it, you know, can and very often does reinforce discrimination and bias. Any biases that are even accidentally part of the data sets that go in can very readily be reinforced coming out, and you know, and there are very, you know, even more serious things that can happen when explicit adversarial behavior comes in, and this is still a very early you know, research topic with a lot of open questions and unsolved problems. Okay. So any more questions? Okay, thanks a lot. So see you next week.